The starting point for this lecture is that I have a sample. I have a statistical model consisting of assumptions about the joint distribution of my sample. Among these assumptions, there is an unknown parameter, theta, which I would like to estimate using my sample. Therefore, I have created an estimator, theta hat, which is a statistic, that is, it's a function of my sample. In this case, I've also added a subscript n to my estimator to keep track of how many observations I am using in my formula for theta hat. We say that this estimator is unbiased if the expected value of theta hat is equal to theta. Being unbiased is a very nice property for an estimator to have. Unfortunately, a very common problem in statistics is that when you try to figure out if your estimator is unbiased, you need to evaluate the expected value of theta hat, which is the expected value of this function. And if your sample consists of continuous random variables, this is equal to an integral over all of Rn g of x times f of x dx, where x now is just the vector x1 through xn, and dx here is just dx1 through to dxn. So this is a multiple integral involving n integral signs, and in many cases this integral is very difficult to evaluate, sometimes even impossible. So in many cases, it is very difficult to check whether an estimator is unbiased or not. Another problem with this criteria, unbiasedness, is that many estimators actually will not be unbiased, but the bias tends to be pretty small and it tends to go away as n increases. Because of this, there is a need for an additional criteria to evaluate estimators. And that is the criteria that we will discuss in this lecture, and we will define what we mean by an estimator being consistent. So the idea is then as follows. We think of the sample size n as an arbitrary natural number. So theta hat 1, that would be the estimator of theta if I had only one observation. In the same way, theta hat 2 would be the estimator of theta with 2 observations, 3 observations, and so on. Since we think of estimators as random variables, at least before we collect the data, this is a sequence of random variables. In general, the higher the n is, that is, the more observations I have, the better should be my estimator. I have more information, so I should be able to make better estimates of theta. If it is the case that this sequence of random variables converges in probability to precisely theta, that is, if the plim of theta hat n as n goes to infinity is equal to theta, then this is a property which is very positive. So in this case, we will say that my estimator is consistent. So based on what we know about convergence in probability, that means that the PDF of my estimator will eventually collapse onto the point theta. For a very large n, I will have a PDF which is very heavily located around theta, maybe something like this. That also means, of course, that as n increases, the error that I will make, that is, the difference between my estimator and theta, will tend to be very small. It also means that if I have an infinite number of observations, then I will know theta exactly. Another way of defining consistency would then be that the probability that the distance between my estimator and the true unknown parameter theta the probability that this distance is less than some arbitrarily small number epsilon will always go to 1 as n goes to infinity for every epsilon greater than 0. Here is the most important example. I have a random sample, then the sample mean x bar will be a consistent estimator of mu. The probability limit of the sample average, just adding an n here because that's the variable that goes to infinity, is equal to mu. As you continue doing statistics, it will become clear that even though the expected value of an estimator, that is the expected value of this function of my sample, may be very hard to calculate, the probability limit of theta hat, which is the probability limit of g of x1 through xn, is very often much simpler. As discussed previously, you will also see that in many cases, the expected value of your estimator is not equal to theta, but you will find that the probability limit of theta is equal to theta. These are some of the reasons for why consistency, these are two of the reasons for why consistency tends to be a more important property of an estimator, at least in more difficult statistical problems.